All right, today we're going to talk about section 2.9, inverse functions. If you'll get your notes out, we can get started. All right, let's go to work. First of all, what is an inverse? I'll spend a little time on some vocabulary today, okay? I think this stuff looks extremely hard. Maybe if you can grab a few simple things, it doesn't get as bad. Inverse means opposite. I say inverse, you say opposite. Inverse. Inverse. I say opposite, you say inverse. Opposite. Opposite. For example, you realize that there's only 4 real operations in math? What are those operations? Wow. Whoa. Crazy look on your face. Like, what are you talking about, man? Only 4 operations, really. We can argue that, too. What are the operations in math? Addition, subtraction. Come on, Katie. What are the other 2? Multiplication and division. What if, now, addition and subtraction are inverses. They're opposite. They undo each other, right? Multiplication and division are inverses. They're opposite of each other. They undo each other. Now, what if I got crazy and told you there was really only one operation? What if I told you the only operation in math really was addition? Agree or disagree? I got one that's agreeing quickly. How many people agree? How many disagree? Okay. Well, let me ask you this. What is subtraction?
Adding a negative number.
Isn't it really just adding a negative number? Yeah. So subtraction is really addition. Just addition of a negative number. Can you accept that? Cole doesn't want to. He wants to fight it. I can tell. Is it true? Will you at least give me that it's true? Okay. I know you don't like it. I can see it all over your face. That's okay. You don't have to like it. All right. So what is multiplication?
Just like faster addition.
Yeah. Multiplication is just repeated addition. 4 times 3 really means 4 plus 4 plus 4. Right? 5 times 10 really means either 5 plus 5 10 times or 10 plus 10 5 times. Right? So multiplication is really just repeated addition. So there's really no multiplication. That's just a shorthand for addition. Well, what's division? You know, you would think division is dividing it up into groups, right? But anytime we deal with fractions, and every number is really a fraction, isn't it? Except for those irrational ones. How do you divide fractions? You told me the other day. How do you multiply fractions, Cole?
How do I divide fractions?
How do you divide fractions? Yeah, you multiply by the reciprocal. Oh, wait a minute. We've already said multiplication is really just repeated addition. So there's my argument to say that there's really only one operation in math. Now, I don't say that to you confuse you. I'm just being a little bit facetious. There are 4 operations. Now, well, what about x squared? What's that? It's really just repeated multiplication, right? Well, what about a square root? Well, what about roots? Well, that's a form of multiplication, right? Or division, yes. All right. Basically, what I want you to get right now is inverse functions are opposite functions, okay? They undo each other. Inverse operations or inverse functions undo something. Like, Well, I don't have any money, or I'd give you some. David, I'd give you $20 if I had it. Man, I don't have any money. Tell you what, David. Just gonna give you my debit card back, so you get all my money. All my money. There you go. Thank you. How'd I give him? What'd I give him? I gave him all $3 I had. And then what'd I do? I took it away. So what did I really give him? Nothing. Because inverse operations undo each other. Okay? To be a little bit more specific, there's the addition or the addition identity. What is the addition identity? Anybody know? It's 0. What do I mean by addition identity? 3 plus 0 is 3. The identity, there's a property, the identity property of addition, that says if you add this number to any number, you get that same number, and that's 0. Just like there's a multiplicative identity, which is 1. Okay? Well, under addition and subtraction, for things to be inverses, you must get that identity. For example, 3 plus some number has to equal 0. 3 plus what number? A -3. So 3 and -3 are additive inverses of each other, right? So if I had 4 times some number, in order for them to be inverses, they have to multiply together to equal 1. Well, 4 times what would get me 1? 1/4. And so you can see that 4 and 1/4 are inverses of each other, okay? Because that's what we're going to be talking about now, but instead of the simple ones, like the addition and multiplication identities, we're going to be talking about inverses, or functions that undo each other, okay? Now, there's the first thing we got to determine in order to just see if it can even have an inverse is that a function must be 1-to-1, okay? Once we determine a function is 1-to-1, I'll teach you how to find the inverse, and then we'll look at the domain and range of a function and its inverse. And of course, we will determine if two functions are inverses of each other. Okay? First, before we can determine or find the inverse or deal with the inverse at all, we must determine if a function is 1-to-1. What does it mean for a function to be 1-to-1? Well, a 1-to-1 function is a function in which every y value of the range is matched to exactly one x value in its domain. What? Well, do you remember way back when we were just determining if something was a function? 0, 1, 2, 3, 4, 5. And we would have like 6, 7, 8, 9, 10, 11. Is that a function? Absolutely. Each input has one output. Could I then do this? Is that still a function? It didn't matter that the y was repeated, did it? The only way I could make this not be a function would be to have a repeated input, yes? Now, is this a function? Still a function because it has that repeated input has the same output, right? Okay. Any other number I put in there, all of a sudden, this is no longer a function, okay? But this used to be okay. That's a function, isn't it? However, that function is not 1-to-1. It's not. What does 1-to-1 mean? Not that every input has one output, but rather that every output also has one input. In other words, these outputs can no longer be repeated either. I like to talk about this 1-to-1 function as being a marriage. Anytime you go outside of the marriage, it ends. You know what I'm saying? 1-to-1. That's it. You've decided forever and always. You're the one for her and she's the one for you. That's how it works. 1-to-1. Okay? Now, so if you're looking at a table or an equation, basically you can't have any repeated outputs at all. Okay? The other thing that works on this 1-to-1 is there, you know how we used a vertical line test to determine if something was a function? We now have a horizontal line test. The horizontal line test works exactly the same as the vertical, except that it's horizontal. And this tells us whether our function is 1-to-1. For example, this function given to us fails. Therefore, it is not 1-to-1 function. Cool? So if you have a graph, you can use the horizontal line test. Or you can just take whatever function you have and graph it. How about this function right here? Let me go with another color for the function. Is that function 1-to-1? Absolutely. Passes the horizontal line test. Okay? And the horizontal line test is a function is 1-to-1 if no horizontal line intersects the graph of the function in more than one point. Let's look at these three examples. This first one, is it 1-to-1? No. How about y? Is that 1-to-1? Or the second one, is that 1-to-1? Yes. And the third one, is that 1-to-1? Well, it is 1-to-1, but it's not actually a function, is it? So what do we call this thing that's not a function but is 1-to-1? It's a relation. Okay, it's a relation. Not that big a deal, but it's not a function, but it would pass the vertical line test. It can be so. You can have something that's not a function still be 1-to-1. But if it's not a function, we're not going to really be doing anything to it or with it anyhow. Okay? How about these? Example 2. Example 2. If we look just at this first one, is that a function first? Yes. I look at the domains, and each one only has one line going from it. So yes, it's a function. Is it 1-to-1?
Yes.
I look at the range then, and each of these input or outputs only has one line coming to it. Does that make sense? Let's look at the second one. Is this a function, first of all? Function? Yes. Each input has one output. Is it 1-to-1? Oh, so let me do this again. So we look here to see if it's a function. And then we look at our y's to see if it's 1-to-1. Okay? This one is a function, but is not 1-to-1. How about this last one? Is it a function? No, because this one has two outputs. But is it 1-to-1? Yes. See the difference? All right. Any questions on what a 1-to-1 function is? Each output has exactly one input. So isn't that funny? We're talking about inverses here, right? And we learned about a function way back in Algebra 1 being each input has exactly one output. And now we're learning about inverses, and guess what? You just switch those. Each output has exactly one input. Isn't that funny? It's the opposite or inverse of what we learned in the first place. Boy, I better put my money up here before Davey takes it all $3. All right. So now let's find the inverse of a function. Okay, let's find the inverse of a function. First, let's assume that they're one-to-one. Okay, and here is the function notation for an inverse, f of negative 1. Then f of x equals y if and only if, there's another phrase that you're going to start learning, if and only if the inverse of y, or the inverse function of y, equals x. Check this out. Check this out. The input has to equal the output, and then you switch those places. Then the output equals the input. What does that mean? It means if I input some x to the function and I get the output y. So let me give you an example. Let's say I input 3 into some function. And the output I get is 4. Okay? For the inverse to work, the y, or the output, now goes to the input of this new inverse function. So if I input 4, what am I going to get out? 3. That's what inverse functions do. If you put in one thing, whatever output you get, you should be able to switch those. Notice in this switching thing here going on, yes? The switching, the x and the y, that's going to come back to us in a second. And then, of course, if we do both functions. Now, what operation is that little sign right there? Of, the composite function, right? Anytime you do the composite function to any input, to any number, and you do the composite of those two functions to it, look what you're getting out. The exact same number. That's how you know they're inverses. Okay, now we're going to learn how to find that inverse and see that that's true. But quickly, let's look at example 3 down here. If I take some function and I input 2, I'm getting out 7. So when I use the inverse and I put in 7, what am I getting out? 2. Cool. If I have some inverse function and I put in 4 and I get out 7, then I do the original function and I input 7, what am I getting out? Boy, that's pretty easy, yeah? Inverse functions. They are opposite. They undo each other, okay? Now, there's another kind of way to think about inverses, and that's graphically, okay? And from a graphical standpoint, inverse operations are reflections of each other. They're what? Reflections of each other across this line. That line. What line is that? That's one of those common functions you should know. It's y equals x. It's the parent linear function. Okay? It's the parent linear function. Now check this out. When I say they reflect over each other, look at this point right here. 3, 4. X is 3, y is 4. The input is 3, the output is 4. We've already said when we're dealing with the inverse, those things should be what? Opposite or flipped, right? Look at the mirror image of it. 3 now becomes the output. The output becomes the input. Do you see that? And that's always the case. So graphically speaking, man, this thing's really easy to do. You just flip your numbers, change your numbers. Look, Negative 1, 2, 2, negative 1. Negative 5, negative 3, negative 3, negative 5. And that will get you the reflection over the linear parent function. Okay? So let's go with another example. If we have these 3 points and they're in a one-to-one function, name the 3 points on the inverse. Well, what will this point be? Anybody? 2, negative 1. What will this point be? And the last one? Cool. Just switch them. Okay? So graphically, it's really easy to find the inverse. Equation-wise, it's a little bit more difficult to find the inverse. Okay? And I know they got a couple hard ones down here, and I'm going to start with something easier for you. Let's say I give you f of x equals 2x plus 4. Let's say I give you that one. Okay? How do we find the inverse? Well, the first thing we're going to do is rewrite the equation with y in place of f of x. So we're going to say y equals 2x plus 4. Well, that was hard. Then we're going to interchange the x and the y. So x equals 2y plus 4. You with me so far? I haven't done anything difficult. Now I'm going to solve that equation for my new y. So I'm going to subtract 4, x minus 4 equals 2y, divide by 2, y equals 1/2 x minus 2. Everybody agree with that? Can you stay with me there? Are those inverses of each other? Yeah, they are. Now, how can I prove that they're inverses of each other? Anybody? I can find f. Now, this actually should be, I should write it like this. Instead of y, I should say, hey, that's f inverse of x. Now, how do I prove that these babies are inverses? Well, I take f. Well, I could graph it, yeah, absolutely. But let's do it equation-wise. F inverse of f of x. I got to compose these functions. Remember the compositions we did yesterday or the day before? So I'm going to start with this f. And it doesn't matter if I go this way or this way. F of f inverse of x. Doesn't matter which way I go. It should work or will work both ways if they're inverses. Are you with me? So let's take this inverse one. I've got 1/2 x minus 2. Put a parenthesis around. Now that's my x for f. So 2 times that minus or plus 4. So let's distribute. That becomes x minus 4 plus 4. Those cancel. So it equals x. And that's what I'm supposed to get. When I get just x by itself, that proves that those are inverses of each other. Cool? All right. Domain and range is no different. Okay? But it should be the fact that the domain of the function is the range of the inverse and vice versa. The range of a function becomes the domain. So I'm going to skip 5 and 6. Let's go to the next page. All right. Now, and I've already showed you how to determine if they're inverses of each other. You take the composite of the function times the inverse, or the inverse times the function. Doesn't matter. Either way, in both cases, you'll end up with x. As long as that's the case, you have inverses of each other. You've already proven that. Couple final examples. If I take F inverse times F of 337, what am I going to get? 337. If I take a function times its inverse times 5 pi, what am I going to get? 5 pi. Okay. Last thing, do you see these two? Here's a function, here's its inverse. If I take a function and this is my input, what's my output going to be? -1. Now for its inverse, what's my output going to be? 0. Do you see that connection? Yes? Okay. And finally, if I take a function, one more time, if I take a function times its inverse times the input, it's going to end up being 200. Cool? Questions, comments, concerns? Welcome to inverse functions, the end of Unit 2. The end of Unit 2.